Hello sir, good evening.
Good evening, sir.
I am not able to hear you.
No, you are not audible.
I am not able to hear you. Just a
Hello.
minute. Hello. Hello, sir. You are saying. Can you hear me
Yeah.
now?
Now I am able to hear you.
Okay. Good evening, sir.
Good evening. Sir, you gave me that email, but the mail I have sent to you it declined actually.
Uh,
Mechanical 12 something that number at the rate of gmail.com.
23591. Yeah.
Yeah. I
It
sent
is
you
my
that mail.
correct email address actually.
Huh?
It is my correct email address. I will just again send you in the chat again.
ठीक है, send me please. Paper here. Mechanical 235. It is not 1. Probably I wrote 1 2 3 something like that.
Okay.
Mechanical 2 3 na.
Yes.
Let me check.
So shall we start?
Yes, sir.
So good evening to this 7th week's live session. So in this week we will be covering some problems related to whirling of shafts, and the other part is basically vibration absorbers. So, uh, so in the lecture sessions, so you might have basically gone through the derivation of how to derive the critical speed of shaft. So, in the problem which is shown over here, in this problem we will be uh, doing the same, basically the same part. So we will be applying it for the basically finding the displacement of the shaft. So in this question it has been given that there is a shaft of diameter 80 mm and it has a length of 1.5 mm, and it carries a disc which has an eccentricity. So let us first draw this system. So let's say if this is a shaft, and let us try to basically draw a disc. Let us say some disc, and so it has some eccentric mass. So let us say the eccentricity E is given by 240 microns. So basically and so it has been asked the displacement of the shaft at a speed which is 0.5 times of the critical speed. So this is basically, the shaft is 1.5 meters long, and it has a diameter of 80 mm. Uh, so the equation for displacement of the shaft, for whirling of the shaft, is basically given by E into omega square. From omega n square minus omega square. So here we have been given the eccentricity E, and it has been given that the speed is 0.5 times the critical speed. So omega n is basically the critical speed or natural frequency. So omega is basically 0.5 omega n. So so we basically get, so E into so omega n square by omega square minus 1, which is, so omega n square, so it will be E upon 3, so I'm actually experiencing some problems in writing down on the using the writing device, so that's why it's taking some time for me to write down. So it will be basically E by 4 minus 1 E by 3. So basically Y will be E by 3, which is 240 by 3, which is 80 microns basically. So when the shaft is rotating at a speed which is half of the critical speed, the displacement of the shaft will be 80 microns. So now let us move on to another problem, which is related to vibration absorbers. So in vibration absorbers, when they will be used when we want to absorb the vibrations, which is basically if some machine is operating at a certain speed, and if we want to avoid unnecessary vibrations of the machine uh, when it is like the machine is operating near its natural frequency. So then the vibration absorber provides an additional path for basically for the kinetic energy, and it basically the vibration absorber actually oscillates with higher amplitude, and basically tries to force down the amplitude of the machine which we want to avoid from vibrations. So that is the function of the vibration absorber. So in this problem we will be basically going through that similar concept. So it is given that a machine is running at 3500 rpm, and it has been given that its forcing frequency is very near to its natural frequency. So basically 3500 rpm, which is it will be corresponding to the natural frequency of the machine. So basically, let us say if n1 is the speed of the machine, that is 3500 rpm. So basically the natural frequency omega 1 for the machine is 3500 into 2 pi by 60 in radians per second. So it has been given that so when we introduce a vibration absorber, it will basically become a multi-degree of freedom system. So if we like approximate the machine to be a single degree of freedom system, by adding the vibration absorber, we will transform the system into a 2 degree of freedom system. So then the system will have two natural frequencies. So the nearest frequency of the machine, it should be at least 15% away from the forcing frequency. So and for that we have to design a suitable vibration absorber, and the machine mass has been given as 40 kg. So let us say M1 is 40 kg. We can also find out the stiffness of the system by using the fact that K1 by M1 is omega 1 square. So by that we can estimate the stiffness of the machine. Now we have to find out the vibration absorber. So the vibration absorber is tuned in such a way that its own natural frequency is same as the natural frequency of the original machine. So basically K2 by M2 will be the natural frequency omega 2 square is equal to K1 by M1, which is omega 1 square. So this is true for the undamped vibration absorber. So we have to find out basically omega, so using the fact that omega 1 square is equal to omega 2 square, we have to find out K2 and M2. So, so if we represent this system, like if we try to draw a diagram of this system, a simplified representation of it will look something like this. So this part K2 and M2, that is basically the absorber. And this is the machine. So if we try to derive the equation of motion of this system, for that we have to first draw the free body diagram of this system. So basically the spring force will be the only dynamic force acting on this system. So this will be the force acting on this mass, and for the machine we will have the same force K2 into x2 minus x1, and along with that we will also have the other force K1 x1. So now if we write down the equation of motion, so it will be m2 h2 double dot is minus k2 h2 minus x1, and m1 x1 double dot is k2 h2 minus x1 minus k1 x1. So so if we represent this equation in a matrix form, so this will be so let us say if there is some force f0 cos omega t or something like that acting on this mass. So so we get this equation in this form. So mx double dot plus kx is equal to f. So where x is a vector and f is basically the force vector. So now this is a 2 degree of freedom system and it will have two natural frequencies. So here what we have to do is we have to derive the natural frequency of this system. So for that what we have to do is we have to substitute a solution of the form x is, let us say, some x naught e to the power of lambda t, and for finding the natural frequency we will have to ignore the right hand side. So we will get the equation in this form. So for that we basically have to find out. So for this to have a non-trivial solution, the determinant of this matrix m lambda square plus k is to be 0. So using that, if we solve for lambda square, so we will get the determinant in this form. So basically so if we evaluate this determinant, so we will get the determinant in this form. So if we expand this determinant and simplify, so we will get basically m1 lambda square plus k1 plus k2 into m2 lambda square plus k2 minus k2 square is equal to 0. So this will be the expression for the determinant. So and by equating the value of the determinant to 0, we can basically solve for, so it will be a fourth degree equation in lambda. So it will it will look something like this. So m1 m2 lambda to the power 4 plus m1 k2 lambda square plus k1 plus k2 into lambda square minus, so plus k1 plus k2 into k2 minus k2 square is equal to 0. So this will be the expression for the characteristic equation. So if we divide on both the left hand side and right hand side by uh, by m1 m2. So we will get lambda to the power 4 plus k2 by m2 plus k1 plus k2 by m1 into lambda square plus k1 k2 upon m1 m2 is equal to 0. So using this we can basically derive the natural frequency in terms of k1 k2 m1 m2. So now we will not be given k1 k2 k2 and m2. We have to find out that. So we have been given k1 m1. So k1 m1 will be known. So k1 by m1 is basically omega 1 square, and k2 by m2 will be omega 2 square, and let us assume that m2 by m1 are in some ratio, let us say mu. So then this equation will get simplified to omega 1 square omega 2 square is equal to 0. So this will be basically the characteristic equation for this system, and so using that, so we will basically we can get, so if we know, so for that we have to design a vibration absorber. So omega 1 square and omega 2 square will be equal. So so omega 1 square is equal to omega 2 square is equal to, so that is one thing that we know. And so we can find out basically, so for designing the vibration absorber we have to find out the value of mu, and so here so we have to basically use this equation to, let us say, if omega square are the so omega is, let us say, the natural frequency, so lambda square, so we will get basically two roots, let us say omega 1 which are corresponding to omega 1 omega 2 are basically the natural frequencies. So these are the two natural frequencies of the system. So now if we now look at the problem of forced vibrations for the system, so considering this force vector on the right hand side, and then if we try to solve for the displacement, let us say x1 and x2, when it is going through some forced vibration, so we will get the equation so the mass and stiffness matrix, and this is the force vector F. So if we assume the force vector to be of the form F is some F naught e to the power j omega t, and the displacement x also to be of some of the form x naught e to the power j omega t, then we will get minus m omega square plus k x naught. So that will be f naught. So e to the power j omega t will be the same on right hand side and left hand side, so we can just leave it. So to find out the amplitudes or amplitudes of the displacements x naught, so we have to find out minus m omega square plus k inverse into f naught. So that will be so we have to basically find out the inverse of k minus m omega square. So it will be minus m2 omega square. So basically this is the matrix m k minus m omega square. So and so by so how so we have to calculate its inverse. So we basically get k2 minus m2 omega square k2 k1 plus k2 minus m1 omega square, so divided by the value of this determinant, so it will be m1 m2 omega to the power 4 minus for this vector into naught comma 0. This will be basically the vector x1 x2. So the amplitudes of the vibrations. So for designing the vibration absorber at resonance, so at the when it's operating at the resonant frequency of the original machine, so then for that basically we can, so here it has been given that our machine is operating at its own at near its natural frequency. So we can use this fact over here to solve this. So we have been also given that our natural frequency should be 15% away from the original natural frequency. So omega should be either 0.85 times, say omega 1 or omega 2, whatever, because they are equal, for it to be 15% away. So it can be either 15% less than that or 15% more than the omega 1. So let us say we assume here that it is 0.85 times omega 1, and if we try to solve this, so if we simplify this equation by using the fact that k1 by m1 is k2 by m2 is equal to omega 1 square. So then we will basically arrive at the equation of the form So this is the form in which we will get the equation, and if we assume that omega by omega 2 is 0.85, then we will get, so 0.85 to the power 4 0.85 square plus 1 is equal to 0. So now we can solve this equation to get the value of mu, which is basically the ratio of mass of the absorber to the mass of the machine. So we will get mu is equal to 1 plus 0.85 to the power 4 divided by 0.85 square minus 2. So using this we get the value of mu to be about 0.1066. So this is the value of mu. So mu is equal to m2 by m1. So m2 will be into the mass m1. So the mass m1 is basically 40 kg. So it will come to be about 4.263 kg. So that is the value of the mass m2, and we can find out k2 by using k2 by m2 is equal to omega 1 square is equal to omega 2 square, which is 3500 rpm to 2 pi by 60, that converted into radians per second, the whole square. And so using that we will get the value of k2 to be about 572.67 56 kilonewtons per meter. So this is how we basically get the value of basically the mass of the absorber and the stiffness of the spring. What we have used is basically we have just used the characteristic equation of the 2 degree of freedom system and substituted that the value of omega. So for the roots of the characteristic equation, let us say some omega 1 or omega 2, whatever, so then that will be either 15% less than or 15% greater than the natural frequency omega 2. So that's how basically we have derived that. And so any questions on this?
No, question is not there, but so lengthy, sir, very lengthy. Huh?
No, I actually just tried to do the basic derivation also. So we can just use the direct equation also, but like just for completeness I also tried to derive everything from scratch.
Acha. Because in 3 hours I think we have to solve 70-80 questions, no? Some 70 questions, something like that.
Yeah, right. So for exams you can directly use the whatever equations that like we have, but for learning purpose we can just try to derive whatever.
Yes. Still I don't know that because I am not the part of that discussion forum.
Okay.
Whether they are supplying the formulas to us, or shall we carry that formulas with us? So what to do? Because n number of formulas are there, and it is difficult to remember all these formulas at a time.
Okay. Maybe I will
Do you
check.
have any idea regarding this?
No, I am not sure about that. I think it will be like the. So, like, are you not able to access the discussion forum of the course?
No, accepted means I received the mail, okay, but in that mail I have not seen that discussion forum and select that discussion forum and all that thing. Nothing like that. Only
Okay.
I have received that mail, something like that, but I'm not sure about it, whether it is the same mail which you are expecting.
Uh, yeah, you get all the emails, like if whatever all other students ask questions and all those things, do you get those email notifications?
Because I want to make that clear before.
No, do you get emails related to the course? Like,
Yeah, I got the mails.
so I think then you will be added to the discussion forum. So you can actually just ask. So there is in the course you will see ask a question, some tab like that. So you can use that to post your
No,
question.
that tab I have not seen. That's what I'm telling.
Okay, fine. I will show you at the end of this session. So
Okay,
you can maybe
No.
follow that way.
Uh-huh.
Sure. So then we'll proceed to the next question. So it's basically similar. So we have been given that a rotating machine is supported on a pedestal, and it basically induces vibration into the surrounding area through its pedestal mount, and it is operating at a speed of 4000 rpm. So we have to find out the mass and stiffness of the vibration absorber, and we have been given that the magnitude of the exciting force is 300 newton, and the amplitude of the auxiliary mass has to be limited to 2.5 millimeter. So here we have to use this similar approach that we have used in the previous uh, question. So, we have to solve for the displacement of the vibration absorber. So we have to solve basically this equation, minus m omega square plus k x is equal to f. So x is basically the displacement vector and f is the force vector. So x is basically x1, x2. So x1 corresponds to whatever the machine, and x2 is for the absorber. So the expression for x2, if we solve for this, will come out to be k2 f naught. So this will be basically by solving along that vector equation, like matrices and determinant and all. Like we have to find out the inverse of this matrix m omega square plus k. So right now we have discussed those steps in the last question. So I'll skip those steps and just directly write down the final expression. So it will be so this is the expression for the displacement. So now if we further try to simplify this, So if we normalize this by the static deflection, so x2 by f0 by k1, so we will get the expression of the form. So if we, there are several steps in simplification, so but basically I will just write down the final result for now. So this will be the simplified expression for x2, the displacement. So here we have been given that omega 1 is 4000 into 2 pi by 60, and we have been given f naught is 300 Newton. So this will be basically, so magnitude of this is mod of this basically. Uh, so we have to find out mu again in this question. So we have been given that the displacement x2 is 2.5 mm. So in this expression, if we substitute that the machine is operating at 4000 rpm, which is omega 1, which is the natural frequency, so we will get basically x2 upon f0 by k1 is 1 upon, so basically we are using omega is equal to omega 1, which is equal to omega 2. So then our expression will get so modulus of that is 1 upon mu. So we will get the value of mu as So how do we find out K1 now? So we know that the mass M1, so that will be using uh, using the weight of the machine of 2000 Newton. So from that we will get, so value of G, if we substitute it as 9.81, so from that we will get the value of mass M1, and K1 will be basically M1 omega 1 square. So mu will be F naught upon x2 into M1 omega 1 square so so we can get the value of mu as 300 divided by using 2.5 mm as x2. So substituting its value in meters, so the value of M1 will be 2000 by 9.81, which is 203.87 kg. And omega 1 square, so we can substitute so by solving all this we can get the value of mu, which is equal to 300 divided by 203.87 into 4000 into 5 by 60. So M2 will be mu M1, which is so we should get around 0.684 kg. So that will be the mass of vibration absorber. So So this is how we can basically use the characteristic equation of the vibration absorber to, and also its like equations of displacement for post vibration, to find out the different uh, quantities. So any question on this?
No, no.
Okay. So then I will just quickly show an animation of the vibration absorber, how we see basically the vibration absorber uh, function. Uh, so can you just confirm whether my screen is visible?
Yeah, yeah. This is visible.
So, so here like I have basically tried to prepare an animation using MATLAB. So if we
Mhm.
consider the same 2 degree of freedom system that we had considered in the previous class, like the quarter car model, so similar 2 degree of freedom system. So here we also included damping. So the mass m1 is acting as the vibration absorber, whereas the m2 mass, let us say it is a machine, it is heavier, so it weighs 2000 kg, and the mass and the stiffness, like basically m1 and k1, it is chosen such that k1 by m1 is k2 by m2, and the damping is chosen arbitrarily. And let us say if there is a force, sinusoidal force f naught cos omega t acting on this mass m2. So here I have tried to simulate using MATLAB how the amplitude of the oscillation of the masses m1 and m2 will change when as we vary the frequency of the sinusoidal forcing. So uh, here so this graph shows the plot of the amplitude versus the frequency. So it is plotted on a log scale. So we can see that uh, so basically it is chosen that the natural frequency, it's around 1 hertz, so 10 to the power 0. So at that we should see that peak. So the blue curve is just the response of the single degree of freedom system, just the machine without the vibration absorber. So after adding the vibration absorber, uh, we see basically the two different curves, the orange curve and the red curve. So the red curve is basically the the amplitude of the mass m2. So we can see that there is a significant dip in the amplitude. So basically I am pointing to basically pointing to this red curve uh, near 1 hertz. So we see that there is a dip in the amplitude at near the frequency of 1 hertz. By adding the vibration absorber, so we are avoiding the high amplitude oscillations of the machine at that. So instead of that, we see two other peaks, but they are also of relatively lower amplitude, and the vibration absorber's amplitude is given by the yellow curve. So that is like much higher than the amplitude of the machine. So we can see how, like qualitatively, like basically using this curve, we can see that now we will see just an animation of the vibration absorber, so at different excitation frequencies. So as we vary it, let us say from zero point 0.1 hertz, then we will see its motion near 1 hertz, and then after basically after it has passed the natural frequency, we will see three different behaviors. So if we animate the motion we can see that there is no appreciable motion. So as like initially there are some overshoots, but after some time, like after a few seconds, we can see that both the uh, absorber as well as uh, the mass are basically moving at very small amplitudes. So basically at in about 15 seconds or so, it settles down into its both the masses vibrate along at the excitation frequency. So this is the plot of the displacement, velocity and acceleration versus time at the excitation frequency of 0.1 hertz. So now when we see the motion near 1 hertz, which is close to the natural frequency, so then now we will see how the vibration absorber behaves. So this is close to the natural frequency of the machine, but now we see that this lower mass is actually oscillating at much smaller amplitude, whereas the vibration absorber is actually oscillating at much larger amplitude. So that is basically taking away the greater part of the kinetic energy and preventing the mass, basically the machine, and protecting it from high amplitude oscillations. So this is how the vibration absorber will work even when the machine is operating close to its own natural frequency. So it will oscillate at higher amplitudes but prevent the machine from oscillating at high amplitude. So this animation basically demonstrates the working of this vibration absorber close to its natural frequency. So this is the similar plot of this when it is close to the excitation frequency. So we see that the system settles down to the amplitudes of the oscillation as per the excitation frequency, and we see that the amplitude of mass m1, which is basically the vibration absorber, that is much higher than the mass m2, which is the machine. So it successfully performs that function of preventing the high amplitude oscillations of the machine. So now if we move on to a higher excitation frequency, which is beyond the natural frequency of the machine, so then we will see that the amplitude of the vibration absorber is actually much lesser than the original machine. So here it does not perform its actual function. So we can see that the lower mass is actually oscillating at a higher amplitude now. The vibration absorber is actually working in
No, sir, yellow color is representing what? Yellow
Sorry?
color curve.
Here yellow color is basically the vibration absorber's amplitude, and red curve is the machine original basically system.
Original machine. Then blue.
Blue is basically without the vibration absorber.
Acha. Without the vibration absorber.
Right. Yeah.
Got it now.
So basically,
Very nice. This curve is very good.
Sorry.
The curve is very good. Understood
okay.
it clearly now.
Right. Thank you.
So when we use absorber, so its vibration is reduced. Okay.
Yes.
That red color indicating.
Yes.
And machines vibrations.
Yes.
And the vibration of the absorber is high, so it's fluctuating more.
Yes.
But as the frequency goes on increasing, the yellow color is coming down.
Yes.
So its amplitude is reduced, as you have shown now.
Yes, yes,
Okay, 10 hertz.
yes.
Acha. Got the thing.
So this is basically just
Understood.
a small demonstration of how like we can use MATLAB to show that.
Hmm.
So here as well,
Hmm.
like on a time based plot, so we can see that the displacement of the uh, mass m2, basically that is much smaller, whereas m1 is like higher, because of the uh, like basically the characteristic of the vibration absorber, so it actually oscillates at a lower amplitude. So that's all from my side for today. So I will be sharing these slides later, uh, and you can access them from the course website. Uh, so any questions? Uh,
No, you told me now that you will show that
yes, yes,
tab. Hmm.
yes, yes. So I'll just quickly show you the
Yeah,
course
yeah.
page. Uh, so I have opened the course page. So here on the main page you will see all these tabs. So announcements about the course, ask a question. So this ask a question is basically that discussion forum. So on the announcements page, whatever that is posted, you will be receiving emails about that. And ask a question is basically the discussion forum,
Ha,
and
ha.
that will
I actually downloaded this app, Swayam's app, on my mobile.
okay, okay.
Hmm.
So
That's
it will
why I think
also
I
have similar. It will also have similar kind of structure.
no ask the question. I will check once again in that.
Should have that.
Otherwise, on the screen it will be there. No, okay, on what we call it. Yeah, desktop mode. On the desktop mode, I will get that.
Right.
Hmm. ठीक है sir.
It
Thank you.
will be there in
Hmm.
the phone as well, like in the phone app as well. So I also have that.
App Swayam app, no?
I
Where
also
is
have
where is
that
that
Swayam
then?
app. So
Where is that?
I'll also try to show you whether.
Correct.
So here in this, uh, so you can go to the course,
Hmm.
and yeah. So here on the right hand side you will be having
Ask
this
a question.
ask a
Yeah, it is
question.
there. Yes. Definitely, I will use that.
So I
ठीक
think
है.
it
Thank you.
works only on the desktop site.
Desktop side, no?
Yeah, so I think it will
Desktop side. Please enable the desktop side. That's right.
yeah, yeah. So but you can access it
Okay.
from here as well.
Okay. Let's see. I will check that. I will check.
Sure.
ठीक है. Thank you, sir. Okay.
Yeah.
Thank
Welcome.
you.
Sure. So then we can end this meeting.